we've seen that alkenes can be hydrated to yield alcohols, and that can happen through Markovnikov addition with carbocation rearrangement using dilute sulfuric acid, Markovnikov addition without carbocation rearrangement by oxymercuration demercuration using mercuric acetate followed by sodium borohydride, or anti-Markovnikov addition by hyperboration oxidation using borate THF complex followed by oxidation with hydrogen peroxide. Now I want to turn our attention to the hydration of alkynes, the carbon-carbon triple bond. The hydration of alkynes does not yield alcohols. It actually yields aldehydes and ketones. The aldehyde would be the product of the anti-Markovnikov addition, and the ketone would be the product of the Markovnikov addition. And the reason for this change, the isolation of carbonyl compounds instead of alcohols, is that enols are not stable. And in the presence of either acid or base, an enol will undergo an equilibrium to the more stable carbonyl compound. And this is true whether it is a terminal enol like this one or an internal enol. So there's an equilibrium process that results in the transfer of the hydrogen from the oxygen to the adjacent carbon and the production of, in this case, the aldehyde. This equilibrium happens in either acid or base, and because the carbon-oxygen double bond is significantly more stable, it always lies towards the carbonyl compound. There are a couple of exceptions that we'll see in the second semester course where an enol can be stable if the double bond is part of an aromatic system, like in the compound phenol, or if it's conjugated with another carbon-oxygen double bond. But for our purposes this semester, enols are never going to be stable. They're always going to end up yielding the more stable carbonyl compound. And the mechanism is actually pretty straightforward. In acid, it behaves an awful lot like the monoaddition product of HBr across an alkyne, right? Where you have a bromine here that's able to stabilize a positive charge. The pi bond can attack the hydronium ion, and it will generate the carbocation that's adjacent to the heteroatom with the lone pair, because that allows a stable resonance structure that puts the positive charge on the oxygen. And resonance stabilized carbocations are always more stable than carbocation that's stabilized solely by hyperconjugation. So in step one, we protonate the pi bond. The pi bond attacks the hydronium ion. And then in step two, we deprotonate an oxygen, thus regenerating the acid catalyst. And generating the carbonyl compound, in this case an aldehyde, but it would work the same way if it was a ketone. And you can show the deprotonation step either from this intermediate or from this intermediate. It's just a matter of whether this arrow would start at the lone pair or at the pair of electrons bound to the hydrogen. Now, under basic conditions, we would do these two steps in the opposite order. Instead of protonating at the pi bond and deprotonating at oxygen, we would start by deprotonating the oxygen to generate an enolate ion, and then that substance would protonate at carbon, and again, we regenerate our base catalyst. So the fact that this process occurs spontaneously, it's called a tautomerization. And it's two steps, whether it's in acid or base. protonation and a deprotonation in acid and a deprotonation of oxygen followed by protonation of carbon in base. So the keto and the enol versions are called tautomers. This is the enol. This is the keto form, even though it's an aldehyde, while the keto form is always the dominant form. So if we have a terminal alkyne, like 1-pentyne, we can add water either in a Markovnikov fashion or an anti-Markovnikov fashion to generate pentanone or pentanal. In both cases, we've added water, but you'll notice we've added the 2 hydrogens to 1 carbon and the oxygen to the other carbon. The 2 hydrogens to this carbon, the 2 carbon in 2 position, and the oxygen to the other, which is different from when we were hydrating alkenes, where we added the hydrogen to one end of the pi bond and the oxygen to the other end of the pi bond. The anti-Markovnikov addition happens under basic conditions. In the second step, which means that you're working with an enolate ion. And the, move the R, didn't need to. And the Markovnikov addition happens under acidic conditions. Which means the enol will be an intermediate. But in both cases, it's possible to see a tautomization. In the case of the enolate ion, it's actually going to look like that, right, where the negative charge is distributed over both the carbon and the oxygen, and so you'll protonate it on the carbon to generate the more stable carbonyl compound. So you might think, okay, so what kind of reagents are likely to allow us to accomplish the Markovnikov addition of water across the triple bond, or the anti-Markovnikov addition? And perhaps we can use our knowledge of what happens when you're doing an anti-Markovnikov or a Markovnikov addition to an alkene to predict what might be the reagents. It'll be mercury again, but this time mercuric sulfate, which is actually ionic, where it's mercury 2+ ion and SO4 2- ion in solution, and sulfuric acid and water. There are discrete carbocation intermediates in this. But because of the stabilization of the carbocation by adjacent oxygen, you won't see carbocation rearrangements as you would with the alkene. So it's just one step. It's not 2 steps. It's catalytic in mercury, the full equivalent of mercuric acetate, because you actually end up with an organic mercury compound as an intermediate. And it undergoes the keto-enol tautomerization like this in the final steps. For this anti-Markovnikov addition, we might think that borate would work again, and it does. It's a hydroboration oxidation, the difference being that our borate now has just 1 hydrogen on a boron. Dicyclohexylborane is one of the possible reagents. And it's the one that's used in our text. And then the second step is basic hydrogen peroxide as it was before and undergoes the same mechanism as for the alkene from the intermediate alkynyl borate, which is the product of the hydroboration step. And since it's the same mechanism as on, and that will end up being tautomerized to aldehyde. Another reagent that's commonly used is called 9-BPN, and that stands for 9-bora bicyclo nonane. So the acronym comes from the B for bora, the B for bicyclo, and the N for nonane. It shares with disulfurhexylborane the characteristic of having only one hydrogen attached to the boron, which means we don't end up getting a 3-to-1 stoichiometry. We only add one alkene across it, and having some steric hindrance. And it looks like this. It's a boron that's bridging between two rings. So this ring would be numbered 1, 2, 3, 4, 5, 6, 7, 8, and then the 9 position is this bridge. It's a bridged bicyclic structure. It's an 8-member ring. You could also draw it in planar form looking like this, where you've got a pH bridging across the position from carbon 1 to carbon 4, sorry, to carbon 5. So it's basically 2 cyclohexane kind of rings. Make that look a little less like barium with one hydrogen. It's kind of like dicyclohexylborate, except now the boron is bridged. And it's often abbreviated so we don't have to draw that whole molecule by drawing kind of a little parachute like that. The important characteristics of the boron reagent is there's just one hydrogen, which means we can only add one alkyne to it, and it's sterically hindered. So we can only add this to one alkyne, and it's sterically hindered, so that we're not going to take the intermediate alkene and add it again. Right? So we don't want to add 2 borons to the same alkyne, and we don't want to add 2 alkynes to the same boron. We want it to be a 1-to-1 stoichiometry. So now let's consider the mechanism of these 2 reactions. Right? You can write these out on note cards as just a reaction, but we want to know how these reactions proceed. And for the anti-Markovnikov addition, we'll see that the mechanism is mostly in the oxidation step again. And the oxidation step has numerous proton transfers and things coming on and falling off boron, whereas the hydroboration step is a single concerted step as usual. Let's talk about the mercuric acid, or the mercuric ion, catalyzed hydration of the alkyne to produce a ketone. Right? And a terminal alkyne. Either hydroboration or or mercuric acid catalyzed reaction would generate a ketone if you had an internal alkyne. No aldehyde is possible in those situations. So the first step, probably not surprisingly, is for the pi bond to attack mercury to generate a 3-member ring intermediate. which now has a 2 positive charge somewhere in the ring. We'll just put it up here as if it were still on the mercury, but it's kind of distributed among the carbons, just directly analogous to what the mercury ion would do in the oxymercuration reaction. The nucleophile, water, is going to attack this the same way it would in the oxymercuration. It's going to attack the carbon with the larger partial positive charge on it, and that's going to be the carbon that has greater hyperconjugation to the propyl group as opposed to the hydrogen. So that's not a surprise. Release of ring strain is a major reason for this reaction to occur. And our intermediate will have a positive charge on the oxygen from the nucleophilic water and the other positive charge on the mercury. The mercury has effectively been kind of reduced in this reaction because now it's bound by the pair of electrons that used to be the pi bond to this carbon. We can have a proton transfer reaction where this hydrogen is removed. To generate a neutral alcohol. And you'll notice that this was an anti-addition, although that's not particularly relevant in the final product, because the final product will be a carbonyl compound. In the presence of sulfuric acid, this pi bond can get protonated by the hydronium ion to generate a resonance stabilized carbocation. With carbocation on the position right next to the oxygen. And what happens next is the mercuric ion simply falls back off, returning this pair of electrons to the pi bond. To generate enol. And return the mercuric ion. Right? So this is why it's catalytic in mercury in this case, because the mercuric ion falls back off again. So the first step, right, is attacking the mercury electrophile. The second step is to open the 3-membered ring. Which is the origin of the anti-nature of the addition. Third step is a proton transfer. The fourth step is another proton transfer. So we've taken the proton off this oxygen and then added it to the carbon. And then step 5 is for mercuric ion to fall back off. And now we have an enol. So what happens next is the keto-enol tautomerism, where the pi bond will once again attack the hydronium ion. Protonate the pi bond. And if you're thinking to yourself that step 6 looks a lot like step 4, it's because step 6 is identical to step 4. The only difference between step 6 and step 4 is whether you have a mercury plus sticking on the terminal end or another hydrogen, right? It's still a pi bond with an OH group on it attacking hydronium ion to generate a resonance stabilized carbocation. So the intermediate after step 4 looks a lot like the intermediate after step 6. All we have to do now to get our ketone product is remove the proton from the oxygen and push the pair of electrons back in to form the double bond. This mechanism is fairly typical of mechanisms that happen in acid solution, in that there are a lot of proton transfer reactions. Right? Step 3 is a proton transfer, step 4 is a proton transfer, step 6 is a proton transfer, and step 7 is a proton transfer. So you've got 4 proton transfers out of your 7 steps. You've got an attack of the pi bond on the mercury 2+, and then you've got a regeneration of a pi bond when mercury 2+ falls off, and then you've simply got one nucleophilic attack in step 2, where we open the 3-membered ring. So you've got 2 attacks of, you've got an attack of a pi bond and electrophile, you've got a nucleophilic opening the 3-membered ring, which is typical of many of these reactions of alkenes that don't involve discrete carbocation intermediates, and then you've got a lot of proton transfers. The discrete carbocation intermediates that we see in this are both stabilized by the adjacent hydroxyl group, and that's why we don't have to worry about carbocation rearrangement, because we have resonance stabilized carbocations, which would be more stable than a carbocation that's stabilized merely by hyperconjugation. So it's 7 steps. It's one reaction, right? It's not a separate workup step like we have in the oxymercuration, and there's no isolable organic mercury compound. Right? We're not going to isolate this intermediate that has the mercury attached because it's still positively charged. What about the hydrochloration oxidation reaction to generate the aldehyde? If you know the mechanism for hydrochloration oxidation for an alkene, you effectively know the mechanism for the hydrochloration oxidation of an alkyne, because with the exception of the tautomerization at the end, the mechanism is the same. So let's start once again with our alkyne, terminal alkyne, 1-pentyne. And now we're going to have our boron compound. And I'll use dicyclohexylborane, but the mechanism would be the same for the 9-BDN. And we're going to have a concerted mechanism where the pi bond attacks the boron, which is electron deficient, and simultaneously the hydrogen attacks the carbon. So this is a syn addition, because it's going to go through a 4-membered ring transition state. And since the nucleophile and the electrophile are both coming from the same molecule, they have to come from the same side. We have a partial negative on boron, and we have a partial positive on the carbon where this hydride is coming. Because this boron in the intermediate kind of has 4 bonds to it, which would be built up by a partial negative charge. The product of this will be an alkyl borane. because we've got steric hindrance here, with these two bulky cyclohexyl groups, it's not likely that this alkene is going to add to another molecule of dicyclohexyl borate to form a diboron compound. And because there's no additional hydrogens attached to the boron, it's also not possible for a second alkynes to add to the boron. So we're going to have these two alkyl groups here and an alkene, and that's going to be the final product. Steric hindrance to prevent the addition of a second borane to the alkene, only one hydrogen on the boron to prevent addition of a second alkyne to the boron. Right? So one-to-one stoichiometry. This is all for step one. A single step, concerted, boron group transition state. And now we undergo the oxidation. The oxidation occurs the same way that it did in the hydration of the alkene, where the first step, or step 0, is just the acid-base reaction to create the hydrogen peroxide anion and water. The hydrogen peroxide anion is now the nucleophile that's going to attack the boron. Generate an adduct that has a negative charge on the boron. And remember, boron doesn't really like to have a negative formal charge because boron is not a very electronegative element, which means that we can now undergo that crucial alkyl shift, kicking out hydroxide ion and generating the carbon-oxygen bond. Generating that carbon-oxygen bond with retention of stereochemistry. Which means that the oxygen and the propyl group will be trans to each other on that double bond. Hydroxide will now attack the boron. Once again, generating a negative charge on the boron. Which it's not particularly happy with. So we go through these intermediates that go back and forth from having a trivalent boron with an unfilled octet, which is not happy, and having a tetravalent boron with a negative formal charge on boron, which is also not happy. What can happen now is the vinyl alkoxy group can fall off. To generate an enolate ion. And then the resulting boric acid can get deprotonated. I'm going to show it from the enolate form that has a negative charge on oxygen. Keep in mind that there is a resonance structure that has a negative charge on the carbon. So if you're more comfortable, you can certainly draw this resonance structure and have the carbon anion directly attacking, but I'm going to show the pair of electrons from the lone pair on oxygen coming in to form the carbonyl at the same time as this pi bond removes the hydrogen from the boric acid ester. And that equilibrium lies, because of the acidity of the boric acid, that equilibrium lies way towards the product, the aldehyde. You'll notice that this boric acid anion still has two R groups attached. Those two R groups can also come off as cyclohexanol. So in the end, you'll have BO3 minus and 2 molecules of cyclohexanol in addition to your aldehyde. Generally, alcohols are easily separated from carbonyl compounds by chromatography, so we don't worry about the fact that cyclohexanol is going to be a byproduct. Or in the case of the 9-BBN, we would expect the other product to be (1,5) cyclooctate diol. And BO3 minus. So the oxidation step is the majority of these steps. Step 0, right? The proton transfer to generate the hydrogen peroxide anion. Step 1, the hydrogen peroxide anion attacking boron. Step 2 is the key alkyl shift, right? That's the key step. And then in step 3, step 3, hydroxide ion attacks boron. In step 4, the alkoxide ion falls off. And in step 5, we have that proton transfer reaction where the anion, the enolate ion in this case, removes a proton from the boric acid derivative, taking advantage of the acid-base chemistry. So we have 3 steps that are effectively irreversible. This one, which has an equilibrium constant of 10 to the third. The alkyl shift is irreversible, and the final step, which has an equilibrium constant that's greater than 10 to the third, because the pK of this hydrogen is significantly lower than 22, which is the pKa of 20 or 22, which is the pKa of the hydrogen adjacent to the carbonyl compound. So the mechanism for the oxidation is pretty much the same, except that once you get to the enolate ion, instead of protonating at oxygen like we did in the case of the hydration of the alkene, we're going to protonate at carbon, thus effectively doing keto-enol tetramerization. And that's it for hydration. Right? So we now know we can hydrate alkenes to generate primary or secondary or tertiary alcohols with a rearrangement, and we can hydrate alkynes, terminal alkynes, to generate aldehydes, anti-Markovnikov, using hydrochloration, or ketones using mercuric acid catalyzed hydration.